Now, as we move forward through the chapters, we're actually moving into stuff that every chemist does. Every chemist knows how to do. Every chemist does, usually on a routine basis. Stuff like considering intermolecular interactions, molecular geometry, shape, all that kind of stuff. We do that on a regular basis. And now we're going to talk about this thing called the mole. Now, a mole is a cute little forest-dwelling creature. Likes to burrow and stuff like that. But it's also a name or a phrase we use quite commonly in chemistry. Now, in your notes, please write down chapter 5 and the mole. The mole is a very important concept. Now, I like this picture. I think this picture is kind of neat. Because people think of chemists, they usually think of mad scientists in labs trying to, I don't know, create zombies or something. But most of us don't do that. Most of us lead pretty normal lives. Now this are chemists right here. Well, you'll notice in the back, they have a stand mixer. That's weird. This is not just any ordinary chemistry lab. That's a food chemistry lab. Everything they do in there, they can eat. Cool, huh? That's why they have a stand mixer. Now, she should have her safety glasses on, but for the purposes of the photo, I'm sure they had her take them off. So chemists don't only just work in labs working on drugs and poisons and all kinds of stuff. They actually work in food labs to make products for us to eat. Kind of cool, huh? It would be fun to kind of eat your creations, wouldn't it? Now, when you're counting, and you've all done this, we have words that mean numbers. The most common one is the word dozen. It's a catch-all word. It means 12. So a dozen. You can have a dozen pencils. Everyone knows you have 12 pencils. You could have a dozen students. Everyone knows the word dozen means 12. We've accepted that as a society. Dozen means 12. We also know that a ream of paper is 500 sheets of paper. We've accepted that. If you have 2 reams of paper, you have 1,000 sheets. We just accept that as a society. That's what the number and that word correspond. Pencils, or the word gross, 144. The word gross means 144. These are just words that mean numbers. That's all they are. And that's all the mole is, it too. The mole is simply a word that means a number. Okay? It happens to be a very large number, but that's what it means. A mole is 6.02 times 10 to the 23. 1 mole equals 6.02 times 10 to the 23. Now, if somebody says a dozen, they say a dozen. That just means 12, right? We don't know a dozen of what. They haven't said a dozen eggs or a dozen pencils. They just said the word dozen. So when I say the word mole, I'm just saying 6.02 times 10 to the 23. I've got to give you something else. I've got to tell you what it means. A mole of what? A mole of cars? That's a lot of cars. A mole of students? That's a lot of students. Or, more generally in chemistry, we talk a mole of atoms or ions or molecules. So a mole, usually in chemistry, we're referring to a mole of atoms, ions, or molecules. One of those 3 is usually what we're referring to. Sometimes you'll hear people say particles, but atoms, ions, or moles can be also called particles. So I'm just being more specific. All right? The mole, 6.02 times 10 to the 23, anything. And in chemistry, we're usually referring to atoms, molecules, or ions. All right? So now, if I have 1 mole, say of the element, I don't know, I like gold. Let's talk about gold. If I have 1 mole of gold, I have 6.02 times 10 to the 23 atoms of gold. I got a lot of gold. That's kind of nice, actually. I don't actually have that, though. Okay? So the mole just means 6.02 times 10 to the 23. If I have 1 mole of an element, I have 6.02 times 10 to the 23 atoms of that element. Are you with me? That's all it means. Excuse me. Now, it's a very powerful thing, but we'll get into its power as the day goes on. But we just need to understand that. Okay? 1 mole, 6.02 times 10 to the 23, anything. Now, you can use this as a conversion factor. As it's written right now, it's simply an equality. You've seen this 100 times. It's an equality, no big deal. So we know if we have 1 mole equals 6.02 times 10 to the 23, say atoms, for example, we also know we have 1 mole over 6.02 times 10 to the 23 atoms, for example, or 6.02 times 10 to the 23 atoms over 1 mole. Now I use atoms here. I could have easily used ions or molecules. Depends on what we're talking about. But those are just conversion factors. This is nothing for you guys. From your test results, I can tell you guys that's easy for all you guys. It's just an equality that makes 2 conversion factors. 1 mole, 6.02 times 10 to the 23 atoms, which means 6.02 times 10 to the 23 atoms divided by 1 mole, or you get the idea. Okay? Just a straight up conversion factor. Now the numbers are big, the units are strange, but it's a conversion factor. Okay? Now you saw in the exam that you can use just about any unit you want. We use European dollars. Take that, and you all got it right. Look at that, see? Steaming with pride for you all. Now, let's do this question together. Avogadro's number is used to convert moles of a substance to particles. Avogadro's number, what's that?
That's a mole number.
That's a mole. The mole, 6.02 times 10 to the 23, is also called Avogadro's number. Write that down. Avogadro's number. Avogadro is a human being. He's dead now, but he is the one who discovered that 1 mole is 6.02 times 10 to the 23. So Avogadro's number is this number. All right? That'll be on your formula sheet. You don't have to memorize that. But Avogadro is he's a famous chemist, and he discovered this whole phenomenon of moles. And he related it back, and he did all kinds of experiments to prove it. Now, if we have CO2 molecules, so we have some dry ice we bought from Publix, and we have half a mole, how many molecules is that? Okay? So that's a typical kind of question you might see on an exam. We have half a mole of CO2. So let's just go through this question very systematically. Let's be very systematic. How many CO2 molecules? So molecules is our unknown. And we're told we have 0.5 moles. So moles, 0.50 moles of CO2. So we just wrote down what we need and what we have. Now we also have Avogadro's number, 6.02 times 10 to the 23 molecules of CO2 equals 1 mole of CO2. Okay? I put CO2 in there because that's what we're talking about. We're talking about CO2. You could, if we were talking about a different molecule, you just put the different molecule's name in there. No big deal. Okay. So now we're in moles. Is this all looking familiar? It's kind of the same setup as density, right? Same setup as any conversion that we've done so far. We have moles of CO2 multiplied by some factor will give us molecules of CO2. Okay? We put the moles of CO2 on the bottom, molecules of CO2 on the top. So the moles of CO2 will cancel. Nothing's really changed here, right? Just the units are different, the numbers are bigger. That's it. Don't let that intimidate you. So now we have 0.5 here, and we put the 6.02 times 10 to the 23 there, and the number 1 goes there. Okay? Is that mind-numbing to anybody? It's just the numbers are big. Looks kind of odd. Right? All right. Grab a calculator, crank it out. Or do it in your head. I recommend you crank it out with a calculator. That way you don't make as many mistakes. Crank them out in your head, sometimes you make an error. And on an exam, you don't want to do that, that's for sure. What do you get? 6.02 times 10 to the 23 multiplied by 0.5. Aha! 3.01. Okay, now that's the answer you've gotten so far. But now be careful, there's two significant figures here. So we have to round this to 2. So that's going to become 3.0 times 10 to the 23 molecules. Now, tell me how this question differs from, say, converting densities. Or how does it differ from converting grams to kilograms? Doesn't really. Just the units are different, right? Numbers are bigger. Same steps, same procedure. Same question. Different numbers. Okay? So if I were you, my advice is don't treat questions like they're different. Try to find the similarities and treat them all the same. And that way you can't be wrong. If you always use your units to cancel out, and if your units do cancel out, you're probably going to be right. Okay? Give that one a shot. Number of atoms in 2.0 moles of aluminum is, and now instead of using moles of CO2, you go 6.02 times 10 to the 23 atoms of aluminum equals 1 mole of aluminum. See how this is basically the same expression here? I just changed molecules to atoms, CO2 to aluminum. Why? Because that's what the question is talking about. Okay? So use this conversion factor and solve this question. Most people got it. A few people had just minor mistakes. Nothing to get concerned about, really. Very happy to see that, because this stuff is not hard, but you have to command it. And once you've commanded it, basically everything we're going to teach you in this chapter is relatively easy as long as you can convert. As long as you can convert. Okay, so let's go over this question. Number of atoms in 2.0 moles of aluminum. So instead of molecules, we want atoms of aluminum. That's our question mark. And we want moles is 2.0 moles of aluminum. And we know this to be true. Okay. Now on an exam, I won't give this to you in a question. It'll be on the formula sheet. And it'll say 6.02 times 10 to the 23. It may say particles. It might say whatever. I believe it says anything. So 6.02 times 10 to the 23. Anything equals 1 mole of anything. So it can be any unit you want. It could be moles of aluminum, moles of carbon, moles of children, moles of pencils. It could be anything you want. So you have to know what to put in there. This is in atoms of aluminum, so it's 6.02 times 10 to the 23 atoms of aluminum. Do you feel me? So I can have a dozen atoms of aluminum, right? You know, you could say that. That'd be a little, that'd be very little aluminum, but you could say it. All right, moles of aluminum multiplied by something will give me atoms. Atoms of aluminum. Okay, so moles go on the bottom, molecules go on the top, and we have molecules. We got molecules on the brain today. Atoms. So it's 6.02 times 10 to the 23 goes there, the number 1 goes there, and the 2.0 goes here, and that gives you an answer of 1.2 times 10 to the 24. 2 significant figures, 2 significant figures. Okay? Everyone seemed to really do well on that. And the only thing I would ask you to do is put your units in and make sure your answer has a unit. Make sure you don't leave that out. It'll cost you 1 point out of 5.
Wow.
All right. I told you the units were important. Yeah, go ahead.
With the 24 exponent, when you do that, you just add it and then...
Yeah, well, the calculator would have give, if you'd just done it by hand, you would have done 2.0 times multiplied by 6, which is like 12 basically. So 12 times 10 to the 23. So I made it 1.2 times 10 to the 24. Because if you write this, although correct, the number's right, by convention the decimal point should be here, not here. On an exam I'd give it to you because, you know, exams are worth a lot. On a quiz I'd probably take off 1. Okay? But even then I may not even do it on the quiz. You know, because technically it's the same number, but this is the proper convention. See what I'm saying? All right. Moles of elements in a formula. Now, you guys know, because we've dealt with a lot of them, that most molecules, or most things that we talk about are molecules, and they have more than one atom in them. So let's take the example of aspirin. Aspirin has the molecular formula C9H8O4. So if you take some aspirin, you're taking C9H8O4. Now, you all know, but we're going to talk about it again, that formula literally means in one molecule of C9H8O4, there are 9 carbon atoms. Right? There has to be. Does that make sense? Everyone like that? One molecule, C-U-L-E, of C9H8O4, there are 9 atoms of carbon. Okay? Number 9, there's 9 of these carbons. So in one molecule, you have to have 9 atoms of carbon. In that molecule. They're racing the golf carts. One molecule of C9H8O4 has 8 atoms of hydrogen. Right? Because there's 8 here. So to make one molecule of this, you have to have 8 hydrogens. You must. One molecule of C9H8O4, you must have 4 atoms of oxygen. You must. So now, if I wanted you to build one molecule of aspirin, you'd have to make sure that you have 9 atoms of carbon on hand, 8 atoms of hydrogen, and 4 atoms of oxygen. You'd have to. If you didn't have that exact ratio, you don't have aspirin, you have something else. Okay? So in every molecule of aspirin, there are 9 carbons, 8 hydrogens, and 4 oxygens. Okay? Does that make sense? Everybody? Okay. So now, let's change it slightly. Let's change it slightly. What if I said, instead of one molecule of aspirin, I want you to make 6.02 times 10 to the 23 molecules. I want that many molecules of aspirin. Okay? I just want that many. So that means I have to have 9 times that many, right? Does that make sense? Everybody on board with that? If I want to make this many molecules of that, I have to have 9 times as many molecules of carbon. Because for every one of these, I have to have 9 atoms of carbon. Right? Everybody with me? All right. So it will be 9 times 6.02 times 10 to the 23 atoms of carbon. Does everyone follow this? Everybody. Now the number 6.02 times 10 to the 23 is what? 1 mole. Right? Are you with me on that? So the number 6.02 times 10 to the 23, you could just replace that number with the word mole. Could you? You just take the number away and put the word mole there, right? Does that make sense? Everybody. Somewhat. Okay? So now, instead of saying this, because that's a big number and looks kind of horrible and awful, makes me feel stressed out, I could just say 1 mole of C9H8O4 requires 9 moles of carbon. I could just say that, right? Now what's easier to look at? This or that? Which is easier? The one on the right, yeah? Everyone thinks so? The one on the right's easier to look at. This whole expression means this right here. It means the same thing. We're just writing it in a simplistic fashion because we're human and we don't like too many numbers. It freaks a lot of us out. Okay? So now, if we have 1 mole of C9H8O4, we have 8 moles of hydrogen. If we have 1 mole of C9H8O4, we have 4 moles of oxygen. Okay? Are we on board with that? Everybody, come on.
Yes.
Please tell me. Okay. Now this is not a hard concept, but you have to master it. None of the concepts in chapter 5 are hard, but they all kind of go together. Okay. So now, in this molecule, if I want to make a mole of aspirin, how many moles of carbon do I need?
9.
Everybody? 9. How do we know that? The number 9 right here, right? How many moles of oxygen do I need? 4. We know that from right here. If I want to make 1 molecule of this, I need 9 atoms of carbon, 4 atoms of oxygen. Y'all got it?
Yeah.
Mastered it. Awesome. It's not hard. You just have to understand it. Now, let's work a problem. It's a little bit tougher than that. Okay. Oops. How many atoms of oxygen are in 0.150 moles of aspirin C9H8O4? Now, this question is a little tougher. It's a 2-step question. First, we know how many moles of aspirin we have. I'm sorry, it's not a 2-step question, pardon me. We know how many moles of aspirin we have. Convert that to how many atoms of oxygen we have. In fact, it might be 2 steps. Give it a try. See how you do. Okay? You know, and I'll just leave up the important information. The bottom one's important. The bottom, this is important. You need that to answer the question. And you also need to know that 6.02 times 10 to the 23 anything equals 1 mole of anything. Okay? So yeah, it is a 2-step question. You need to use both of these to solve it. Okay? Give it a try. It's a little tougher, so it might take you a little bit longer, but don't get frustrated. Don't get discouraged. First time seeing something, it's going to be a little bit challenging, that's all. But you can do it. I believe in you. Oh, you can admit if you want. really don't know. No. No, try again. But you're close. You're following the right procedure. Oh, okay. I see. Okay. Yeah. Keep going. I think that's going to work. I think. Don't hold me to that, but I think it's going to work. Keep going. Good. Look at that now. Look at you. Just okay. So that's you're in moles of this, and you just converted it to molecules. So that's molecules of that. So now you got to do one more conversion. Good though. You're on the right track. What's up? Let me see here. Hey, look at that. Okay, so this is converting you from moles of aspirin, and this will be not moles of O, it'll be moles of aspirin.
Yeah.
So then now you're in molecules of aspirin. Now you got to convert to atoms of oxygen. So then there's one more step, but that's not the one.
No.
Nope. So you're in molecules of aspirin. You need to be in atoms of oxygen. If you look down there at the bottom.
So if I bring molecules of aspirin here, why don't I bring it down here and then put the atoms up here?
This would be molecules. Yeah, you put the molecules down here and the atoms up there. Right.
So it'll be 4 atoms of oxygen.
You got it. Just like that, I think. Wait, now, so you converted moles to... Okay, so now you went to moles of aspirin. This will convert you to molecules of aspirin. Okay? Good, though. You're on the right track. It's a little tougher. Don't get discouraged. I know it's easy to get discouraged, but you can do it. You can do it. I don't know. I have to work it out. Something like that. That'll get you there. Hello. So you go from moles, you converted it to... So this is molecules now of aspirin, not atoms of oxygen. You're in moles of aspirin. Okay? How many sig figs? You'd have to be in... 3.
3, it doesn't matter when I multiply.
That's an exact number.
Oh, okay.
4 is an
that's
exact number.
So when I put here this, I have to put 0, 0,
Yep.
6, 0, 0,
Yep.
and then go to 3.
Yes. Absolutely. Good.
I'm stuck.
Oh, you're doing fine. Okay, so now that's going to convert you to molecules of aspirin. Okay? So keep going. You're on the right track. Hi.
When we're doing this, because I got confused on which one I was supposed to do.
Okay.
With the atoms of oxygen, when we're doing this part, do I put aspirin or is it atoms of oxygen?
You have to use the units. That's why you need to, I don't know, what are your units? I can't find them.
4.
Okay, so go ahead and redo this question. Do
Okay,
it.
just
Give
do it
yourself
in my head.
give yourself some more space, and write out your units. It'll help you to. It'll lead you to the right answer. I promise. All right. So how are we all doing? You're confused? Okay, everyone else is too. So you're in good company.
I converted to moles.
Yep.
And I got 0.6.
Yep. Now convert to atoms.
So I just times it times 6 points.
Times 4. Yes, ma'am. Looks right. I don't know if it is, but it looks right. All right, guys. So I've given you a little bit of time to hammer away at that question. It's a little bit tougher. It's not mind-numbingly tough, but it's tougher. No doubt about it. So now, let us just start this question. Now, here's how I would approach it. I would be very systematic. I don't want to make a mistake, so I would be very, very systematic. All right. How many atoms of oxygen? So that's my unknown. So I will just write down atoms of oxygen equal question. Have no idea. moles of aspirin. C9H8O4, 0.150 moles. That's how many moles of aspirin I have. I know that 6.02 times 10 to the 23 moles, of C9H8O4 is 1 mole of C9H8O4. That's pretty much what I know. Okay. Let's be very careful here. Let's not go too fast. Let's go systematic. I am in moles C9H8O4, and at the end of the day, I want to be in atoms of oxygen. That's at the end of the day. Moles of a molecule, and I want to get into atoms of a particular element. Tough question. Well, we can convert from moles to molecules, right? Oh, I spelled it wrong. Sorry. Molecules. Sorry. 6.02 times 10 to the 23 molecules of C9H8O4. So I can convert moles to molecules. I could, right? Most of you did, which was good. So let's say I go from moles to molecules. C9H8O4. So when you do that, when you think about that, take a step back and say, will that get me anywhere? Can I get to where I need to be if I do that? And the answer is yes, because I know if I can get to the molecules, of this molecule, if I can get to the molecules, I can go to the atoms. Now, to go from here to here, I need to use 6.02 times 10 to the 23 molecules equals 1 mole. So I have to use that right here. To go from here to here, I know that 1 molecule of C9H8O4 is 4 atoms of oxygen. So I can use those two expressions to get me where I need to be. It's a little challenging because there's 2 steps. But on the question on the exam, converting for euros and all that, there was like 3 steps to do that, and most of you got it. So I'm pretty sure you guys can handle this question. Now, we're in moles of C9H8O4 multiplied by something that will put moles in the bottom. C9H8O4 molecules in the top. C9H8O4. I'm going to retire this marker. Now, doing this step, doing that step, our units now go from moles of aspirin to molecules of aspirin. Is that correct? Everybody follow me on that? I'm converting moles of aspirin to molecules of aspirin. Okay, that's all I've done. Is everyone confident with that? A lot of you had that done. I saw it on your paper. Okay. So now, I don't want to be in molecules. I don't want to be here. This is not my final destination. It's a stopover. I want to get to here. So I've got to multiply it by something that will put atoms on the top. I need that to cancel out. So that molecule's got to go on the bottom. So now, the molecules will cancel out nicely. And my final answer will be, the units will be atoms of O. I'll get there using this expression. Does everyone follow what I did? A little bit. Not at all. Any answer at all? Yes. 1 person. 2 people. No. Everybody else, talk to those 2 people. They seem to have it made. Just kidding. Everybody okay with this?
No.
What's the problem? Okay. Where did I lose you?
I'm pretty sure if you just done it again, I wouldn't get it.
How about we do this? How about we go through the question, we get the answer, we erase it and do it again? How's that sound?
Awesome.
One person says awesome, the rest of you guys say awesome. What's up?
Would it be okay if you substituted the C98H004 for just the word aspirin?
Sure.
And do it that way?
Yeah. Sure. Just a unit. All right, so we'll do the question, we'll crank it out, we'll go back and we'll do it over again. Just to do it twice. It's always good to do things twice, right? Okay, so now we got to put our numbers in. Right here, the number 0.150 goes there. Here, we have 6.02 times 10 to the 23 molecules in 1 mole. And here we have 4 atoms of oxygen and 1 molecule of aspirin. That's how it should look. So you multiply 0.150 multiplied by Avogadro's number, multiply that by 4. If you got a calculator, crank it out for me. I don't have one. Go ahead.
What if you did it before?
You mean did it reversed? Yes, absolutely possible.
4 times the...
Yep. That should give you the same value. Should give you the same number. As long as the units work.
Yeah, I did the same thing, but in reverse. I separated, but I was
Right.
lost on the unit.
So you convert it moles of aspirin to moles of oxygen, and then moles of oxygen to atoms of oxygen. Yeah. As long as the units work. Yep. Yep. But that way will work because the units will work. I do it this way because I think to me this is more reasonable in my head. Your way is completely logical too. Just I don't appreciate it as much. But it's still right. Okay? So what's the number here? 3.61 times 10 to the 23? I don't have a calculator, so I have to take your word for it. All right. That's how you do it. So why don't you do this? Don't look at my answer. I'll leave it here for reference if you get stuck. Look at the board, look at the screen, try the question one more time. I'll give you 5 more minutes. Now that you've seen it, it shouldn't take you as long. Most questions follow this same type of procedure. Okay? Give it one more try, 5 minutes. Just try to knock it out. But try not to look at the answer. Try to do it just on your own. In fact, this is a really common study technique, is to repeat a question you've already done. Because you'd be surprised that you can't do it. Sometimes it takes 2 or 3 attempts to get the system down. But once you've got the system down, you can own any question.
I did, when I was doing it the first time, I did 1.50 moles times 4 molecules of oxygen. And then I just times it times Avogadro's number, and I got the same answer.
Yeah, the units all work, so the answer should be the same.
Okay. Thank you.
There's always more than one way to approach a problem like this. And as long as the units work, both ways are right. Yes, ma'am?
With this, 24.08, that's the right way to do it with the sig fix since 4 is right.
No, that's an exact number, though. In 1 molecule of aspirin, there's exactly 4 atoms of oxygen.
Okay.
So like in your car, there's exactly 4 tires.
So I would leave it as 24.8.
You'd have to round it to 3 sig figs.
2, 3. Okay.
Yep.
Okay.
All right? Is everyone cranking it out? Just give it a try. Give you a few more minutes and I got to move on because we're a little bit behind today. Or in this class. Happens every year though.
But that's good. We're all doing good in this class.
Most people are, yeah. Which is cool. Makes the job easier and more exciting. You know.
I'm not even good in chemistry and I'm doing good.
See? That's a great testimony. Okay, So take a few more minutes, try to crank it out. If you can't get it done today, come see me after class. I'll go over it with you. Okay? So I just want to move on to get some more stuff put together. Write this down in your notes, please. Molar mass, big, bold type. Molar mass, very important. Molar mass. Molar mass. Okay, so now, molar mass. On the old periodic table, let's come over here and look at this together. On this table, you guys know what everything means. You know what this number is. You know what that number is. You know what these numbers are. You even know what these numbers are. You just don't believe it. You just don't know you do, but you do know what they are. Now, this number down here, this one in red, we haven't really talked all that much about. You know it's a weighted average of all the isotopes and all that kind of stuff, but you don't really know how to use it because we never really talked about it yet. That number is actually, I think, the most powerful number on that table. It's used, in my mind, it's used more commonly than the atomic number. The atomic number of carbon is 6. That's great. But what can I do with that? There's not a lot I can do with it. Knowing the molar mass, which is that red number of carbon, I can do a lot more with that. That's actually a very important number to know. And why is that number important? Well, let me write it down for you. And you can see the units. Once you see the units, you'll know why it's important. So, on the periodic table, carbon has the molar mass of 12.011. So that's just a number. I've told you in this class in the first week, a number without a unit is completely meaningless. So that number is meaningless for right now. But what if I told you this? It's actually 1, not 1.01. .011 grams of carbon is 1 mole of carbon. Now, the mole is not just a mysterious thing that we talk about. Now the mole is actually meaningful. If I wanted to have a mole of carbon, how would I do it? All you got to do is look at the molar mass. If I wanted to have a mole of carbon, I simply weigh out 12.011 grams. If I weigh out 12.011 grams of carbon on a scale, I have 1 mole, which is 6.02 times 10 to the 23 atoms of carbon. If you were to call up a chemical supply company and say, I want 1 mole of a particular molecule, they won't know what to do. Because usually people taking the orders aren't chemists, or they're just people taking orders. But if you tell them you want 12 grams of carbon, they'll ship it to you overnight if you want them to. Because 12 grams means something. 1 mole means something too, but we don't have any scales that are calibrated to the mole. We just don't. But to grams, we can easily weigh out 12 grams. Now, let's go over to the periodic table. If I had a mole of gold, I have 196.96665 grams of gold in 1 mole. That means I have 6.02 times 10 to the 23 atoms of gold. You follow me? Everybody with me on the same page? That's what that number means. So for oxygen, let's just do one more so everyone's clear. Oxygen, we look at the atomic mass of oxygen, or sorry, the molar mass of oxygen. We get 15.9994. So every mole of oxygen okay, 1 mole of oxygen is 15.9994. Pretty cool, right? Yeah?
So 1 atom equal 1 gram?
No, 6.02 times 10 to the 23 atoms is 1 mole. Depending on the element is how much you'd have to weigh out. So for example, oxygen, if I want it 1 mole, it would be 15.9994 grams. Okay, you follow me?
Oh, yes, okay.
if I wanted to have a mole of lithium, lithium's way over here, it'd be 6.941 grams. I have to weigh out that much to get 1 mole. Okay?
So the mass is always going to be equivalent to
The mass is, yes, it's always that many grams in 1 mole. Kind of neat, huh? So now you can relate it back to something that's meaningful to you, which is why the mole was invented in the first place. I think that's freaking crazy cool. All right, so let's go over this real quick. Given the molar mass of each element to the tens place, so 1 decimal point. Just give me 1 decimal point. 1 mole of potassium atoms. Let's just use this table here because it's fast. 1 mole of potassium atoms. Potassium's over here. How much does 1 mole of potassium atom? How much mass is that? 30.1. Maybe some of you can't see it. It's 39.1. Everyone follow me? The mole of tin. Tin's over here. How many grams of tin do I need to get 1 mole of tin? 118.7. Everyone with me? Yes. Calcium. 40.1. So I need 40.1 grams of calcium to have 1 mole of calcium. Is this making sense? Everybody?
Yes.
Everyone on board with that?
Yes.
It's easy, right? You just got to read it off the table.
Yes.
The molecular mass is always in grams per mole, or grams equal 1 mole equals that many grams. Okay? Now, here's the kind of question you can expect. We have the formula C2H6O. I want to know the molar mass of that entire compound. Now, if I just said how many grams per mole is in carbon, you would say 12.011. Carbon's not all that interesting. Things like oxygen, not all that interesting. Things like CO2 now, carbon dioxide, that's more interesting. Things like C2H6O, that's more interesting. That's probably ethanol, by the way. C2H6O is probably ethanol that you drink. You know, it's Friday, so I'm sure, you know, thinking along the same wavelength, right? So now, I have the formula C2H6O. And I want to know the molecular mass of this molecule. I want to know how much that molecule has. So now, I know that that molecule has 2 carbons, 6 hydrogen, and 1 oxygen. Is that correct? Yes. So to figure out the entire molecular mass of that molecule, all I got to do is multiply carbon by 2, hydrogen by 6, and oxygen by 1. That's going to be 2 multiplied by 12.01 grams per mole. This will be 6 multiplied by 1.01 grams per mole. And 1 times 16.0 grams per mole. Now I rounded the molecular masses off just to make the math easier, but that's what it looks like. Okay? So to figure out the entire mass of this molecular compound, 2 times 12.01 plus 6 times 1.01 plus 16.0. So this would be 24.02 grams per mole. This would be 6.06 grams per mole. And this would be 16.0 grams per mole. Add them up. And the answer is 36.1. Oh, 46, thanks. Thought 36 was a little light. 46.1 grams per mole. So now, this molecule, if I have 46.1 grams of C2H6O, I have 1 mole of C2, pardon me, H6O. I also have, if you want to carry this further, I have 6.02 times 10 to the 23 molecules of C2H6 O. Okay? Make sense? So atoms have masses, compounds have masses. To figure out the mass of a compound, simply add up all the parts and pieces, and there you go. It's not difficult, is it?
No.
No. Now, that's about as complex as they'll get on an exam. But in class, I like to do more complicated examples just to make sure everybody can do it. There is it. There it is. What are the molecular masses of those two things? Try doing those two. Now, if you have your textbook, in the front of your textbook is a periodic table. Use that for the molecular masses. I'll write them down on the board here so everyone has the same numbers. Oh, you can do it. Trust me. All right, let me borrow someone's book real quick. I'll give it right back, I promise. And hydrogen okay, please use the numbers on the board so that we can all get the same number rounded off properly. Now on an exam, I'm going to give you a periodic table. Please use the one I give you. Please don't use the one on the wall. You can notice the one on the wall has numerous significant figures in the molecular mass. That's a little bit of overkill for this class. So we won't use those significant figures because it'll drive us crazy. Try to crank those two out. Not too bad. Not too bad. I can promise you'll get at least one question on your next exam that's this, and probably one on your final too. Just simply doing this. So, you know, 5 easy points, right? Please don't give it back to me. That'll get you there. Good. Very good. And that'll get you there for sure. Good. Looks pretty good. Where's your first one? I don't think you are. This is correct, but now this is, you multiplied these two, right?
Multiply or add
No, you didn't add them.
I just add them.
Yeah, you just add them. You multiplied them here, right? This times that is probably that.
No, I just add them, add that and that.
Okay, try it again. This plus that is not 1,200. Oh no, don't divide it. Just add them. You're right. This is this plus this, but if you did add them, that's not the right number. How'd you do?
Try it.
You did what?
I didn't try it.
Okay. How'd you do? Oh, that's your final answer. Don't forget to put the units. Yeah.
Does this 3 goes to all of them?
No, that 3 only goes with the hydrogen and the oxygen.
Oxygen.
Yep.
Okay.
So do you have to add them before? Or
So you multiply yep, and then that, and add them together.
what about this one? Do you have to add them before multiply or multiply separately?
I would multiply them separately, so it's going to be 3 times oxygen, 3 times hydrogen.
Okay.
I would just do it that way. I think that's less confusing, I think.
Okay. But it's the same answer.
You get the same answer, yeah, but you want to just be systematic. That way you don't make mistakes. How'd you do? What was your answer?
The first one there.
Oh, okay, there it is. I think so. I haven't done it yet, so I don't know. How'd y'all do? Looks good. I think so. I really don't know the answer yet. So it looks okay. Don't forget your units, though. Don't forget your units on the second one. Looks okay. How'd you guys do over here? Looks okay?
With the 3, do we use that?
Yep.
Because of OH3?
Yep. So you have 3 times hydrogen, 3 times oxygen.
Oh, okay.
Okay?
Okay.
Get it? Get it? Okay. I trust you. Looks all right. Units are there. Yep, good. That'll get you there. How'd you do? That looks pretty good. They look good. I don't know if they're right. They look good. Yep, looks okay. I have no idea if it's right, but they look like they're being done properly. Oh, here we are. There we go. Looks good. And it looks okay. Yours. Good. All right, so people seem to be knocking this out pretty quick, so that's good. It's not, again, it's not hard. You just have to do it. So let's crank out K2O real quick. K2O is 2 times potassium, 1 times oxygen. So that's going to be 2 multiplied by 39.10 grams per mole, and 1 times 16.00 grams per mole, for a grand total of, what was the answer y'all got? 20 grams per mole.
So on that exam, if you put 94.2, would that be wrong?
Yes, because there's when you add it up, you have 2 decimal points here and here, so you have to have 2 decimal points down here. I mean, would it be totally wrong? Out of 5 points, you get 4, but you don't want to miss that 1 either. Okay, Al, OH to the 3. Now, great questions people had. Well, how do I use that 3? That was a great question. So let's go over that really quick. This formula means I have 1 Al and I have 3 OH minus. Right? That's what this formula means, right? I have 1 aluminum plus 3 and 3 hydroxides. Does everyone agree with that? Everybody on the same page? So then I have 1, 2, 3 hydrogens, don't I? So it'll be 3 times H. I also have 1, 2, 3 oxygens, right? So it'll be 3 times O and 1 times Al. So does that make sense? Now you don't have to break it out like this if you don't want to. You can just say 3 times oxygen, 3 times hydrogen. You can just do it that way. But this means this, so this is why we have 3 hydrogens and 3 oxygens. Is everyone okay with that? Everybody?
Yes.
Okay. So 1 times 1.01 grams per mole. Not 1, it's 3. There we go. 3 times 16.00 grams per mole. And 1 times, what's aluminum? 26.98. For a grand total of 0.10. Oh, 0.1. 0.1 grams per mole. All right. Okay, let's take 10 minutes for a break, and we'll come back and we'll finish off the rest of the day, and then we'll have a good weekend. See y'all in 10 minutes. Hey.
I was gonna wait outside until you had a break.
Oh, you can come right in if you want.
I wanted to ask you a few things.
Yeah.
You still have the packet, right?
We're going to finish it this afternoon.
Oh, okay, yeah, it's due at 4.
Yeah, we'll get it in probably at 2.
Yeah, because Zach and I are working on the other nominations
Okay.
for the advisors.
Thank you.
So I just wanted to make sure you weren't going to turn it in without it, because we have to turn everything in. At
Oh,
the
it has to
same
go all
time.
together?
Yeah.
Oh, yours and ours. Oh, okay.
Yeah, I asked Mr. Pickering and he said, like, please put it all together.
Okay, can you have yours done by 2?
Yeah, of course.
Yeah, just bring it over whenever you have it done. Because I'm sure Dr. Sadiq and I will have ours done probably before 2, because we've already got it done. We're just reading them over. All right, very good. Yeah.
It's just that your nominations are like kind of more complicated because
Right.
you have to put like statements, like student statements, and
Oh, okay.
we aren't even sure how to do it yet
Oh, okay.
because they don't know how to do it. Like the people with student life, I asked, and like they don't know, so I have to wait.
So you have to
for
put in like
someone-
testimonials, you mean?
Yeah, I have to wait for Mr. Pickering to get out of a meeting.
Okay.
To ask him personally.
Oh,
he
he'll-
knows.
oh, there's a specific way they want it written? They don't just want you
Yeah.
to do it any old way, huh? Okay. All right, we'll do your best with that. Thank you.
And I also wanted to ask you, how long have you guys been advisors for the science club?
It's my 3rd year, I think. And his 4th or 5th.
Yeah.
He's been, whatever he is, I'm a year less than him.
Oh, okay. So I
So
have to ask.
I've been here for almost 4 years, so I would be basically 3 years. And he would be 4, I
Do you
think.
know when Dr. Medea stopped being science?
I don't know when she stopped, no. A while ago. So,
All right, I'll
Sorry.
just ask Paul.
all right.
I think he knows.
You may. Sorry.
Okay, thank
See
you.
ya.
Okay, when do you have your office hours
Monday from 2 to 5 in the library.
in the library?
And then Tuesday morning, I think it's 10 to 12:20.
Okay.
And again at 2 to 3:20.
Okay.
On
but I
Tuesday.
like the way you do the calculations because the ones at the library confuse me.
Okay. See you soon. All right, I'll be back. I gotta go to get some water. Oh, I have your graded quizzes here. If you want to grab them while on break.
I have a number too. Call her. No, not that because women. This is a woman. Most of them. You don't really know about the business. Is that?
Doesn't count towards your score. It's just my way of keeping track of who did and who didn't.
Was the whole thing wrong, or was I missing something?
I have to look at it. Come see me after class.
Okay.
Alrighty, guys, let's get settled back in. Try something new. So now, we've learned all about molecular mass. We've learned how to, calculate it from a formula. Now I'm going to show you how to use it. If you have a mass of a sample and you want to convert it to moles, which you will want to do, because moles are where it's at. If you have grams of a sample, you can use molecular mass to convert to moles. Now, on this question, we have a box of salt. And there's like 737 grams of sodium chloride in that container. The question I would have for you is how many moles of salt are in that container? And I will further ask a separate question. How many moles are in that container? And then how many molecules of sodium chloride are there? Those are the questions I want to ask. So, let me just erase this real quick. I want to know how many moles of sodium chloride are in that box. And then I want to know how many molecules of sodium chloride there are. And to further complicate the system, I also want to know how many ions of sodium there are. So we have grams equals 737 grams sodium chloride. Moles is a question mark. Molecules. Molecules of sodium chloride is a question mark. Ions of sodium are a question mark. Okay. We can solve that with just knowing the molecular mass and the weight and Avogadro's number. So now, before we get into the mathematics around this problem, let's just look at something I like to call the molehill. Because a lot of times people get confused or they get kind of nervous when they have to convert grams to moles or molecules because they don't know where to stop, they don't know where to end. So let's just draw this cute little cartoon. This is the molehill. This is the molehill. On one side of the molehill we have grams. On the other side we have molecules or atoms or ions. Okay? So grams on one side, molecules, atoms, or ions on the other. And at the top of the hill there are moles. Okay? That's the molehill. Now, a lot of times people try to go from grams all the way to molecules without first going through moles. So now what happens when you try to do that is right here there's a fire-breathing dragon. And his name is Fred. Fred breathes fire at unsuspecting students. He also has some kind of appendage out here. Resembles a wing, but it's not. It's kind of his death-defying sail thing. Anyway, that's Fred. Fred will burn you alive if you try to go from here to there without going through moles. You must go through moles. You can never, ever, 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 ever go from grams directly to molecules, atoms, or ions without paying the mole price. You have to climb the molehill. Now, just like on the turnpike here in Florida, we must pay tolls.
Not often.
Better hope you don't get a bill from SunPass. They'll get you eventually. Now, grams to moles, what price do you pay? You pay the molecular mass. You must convert using grams over moles. Okay? That's the first price you have to pay. Using the grams over mole conversion factor, you will get to moles. Now, to go from moles down to here, you must use Avogadro's number. Okay? So to go from here to here, you use the grams per mole conversion. To go from moles to molecules, atoms, or ions, you have to use Avogadro's number, 6.02 times 10 to the 23. If you follow that, you will be right, as long as you do your calculations correctly. But your procedure will be correct. Okay, so now we have 737 grams of sodium chloride. I want to know at the end of the day how many ions of sodium I have, or molecules of sodium chloride, depending on how you want to look at the question. So I want to go from here to here. I must go to moles first, right? So let's convert grams to moles. Let's do this part first. So we're going to climb the mountain this way. Pay that toll. Now, we need to know grams per mole sodium chloride. We don't have it. We have to determine it. So looking at the periodic table in your textbook, what's the molecular mass of sodium? And what's chlorine?
35.45.
Add those together. And what do you get? I don't want to do it. Don't feel like it. Just hit the calculator for me. Tell me what that number's. Add them together. Please. 22.99 plus 35.45 equals
58.44.
58.44 grams per mole is the molecular mass of sodium chloride. I just took one sodium, one chloride, added their molecular masses together, and I got 58.44. So now, I'm in grams. I want to multiply by something to put me into moles. Grams on the bottom, moles on the top. I know that I have 58.44 grams, and I have 1 mole. So far, so good. In my grams, I have 737. That's how you'd start it. That's how you'd convert grams to moles. And we used this conversion factor right here, grams over moles. Only this time we had to invert it just to make the units work. Okay? Notice the units cancel. So 737 divided by 58.44 is 12.6. 3 significant figures. 3 sig figs here, 3 sig figs there. Okay, so that's how many moles of sodium chloride we have. So that's moles of sodium chloride. Is that okay? Is everyone comfortable with that?
Yes. Yes.
Few people. At least I've got a few people interested. Okay, so now we're sitting here. We want to get down here, but we're sitting up there now. So we've converted from grams to moles. Now we must convert from moles to molecules using this conversion factor. Okay? Now to do that, I'm going to pop up the screen because I'm out of space. I don't want to erase that just yet. There we go. Okay. So now, we know we have 12.6 moles of sodium chloride in 737 grams of sodium chloride. We've calculated that. We calculated the molecular mass. We've calculated the moles. Now I want to go from moles to molecules of sodium chloride. According to the molehill, I must pay the toll of 6.02 times 10 to the 23. So let's use that. So now I'm in moles of sodium chloride. I'm going to multiply by that by something to put me into molecules of sodium chloride. So I better put the moles on the bottom and the molecules will be on top. That way, the units I do not want anymore go away. The units that I do want stick around. Okay. Thank you. 12.6, and this will be 6.02 times 10 to the 23, and that's the number 1. So I'd multiply 12.6, multiply it by Avogadro's number, please. I don't have a calculator. Whoa. Oh, it's a big number, right? Okay. Better erase that and move it over. Okay, what was it? 7?
24.
So that's how many molecules of sodium chloride I have. So I have that many moles, that many molecules of sodium chloride. Okay? Does that make sense so far? Yep. So we've got 2 of the 3 questions answered. Okay? Now, We want to go all the way to the ions of sodium. Well, that seems difficult, but it really isn't. We look at the formula for sodium chloride, and here's how you should do it. Sodium chloride. We have one molecule of NaCl equals one ion of sodium plus. One molecule of NaCl equals one ion of Cl minus. Right? Every sodium chloride molecule has one sodium and one chloride. That's pretty straightforward, right? Yeah, okay, good. Now, we're in molecules of sodium chloride. Oops, wrong way. I want to multiply that by something that will give me ions of sodium plus. So here I would put molecules of sodium chloride, ions of Na plus. So I know from here, one molecule of sodium chloride, so put the number 1 right here, equals one ion of sodium ion. So put the number 1 right there. And then it will be 7.59 times 10 to the 24, multiply by 1, divide by 1. I get the same answer in ions. Oops. 7.59 times 10 to the 24 ions of sodium plus. Does that make sense? For every one molecule of sodium chloride, you have one ion of sodium. So if I have 7.59 times 10 to the 24 molecules of sodium chloride, I should have 7.59 times 10 to the 24 ions of sodium, because it's a 1-to-1 ratio. Does that make sense, everybody? Yes. So now the follow-up question to that is, how many ions of chloride do I have, Cl minus? 7.5. Should be the same number, right? Yeah. So let's do that out. So if I had 7.59 times 10 to the 24 molecules of NaCl multiplied by one ion of chloride divided by one molecule of NaCl, that should give me, as everyone just said, ions of Cl minus. Now, what if I didn't ask you for either one, but I asked you for the total number of ions? You'd add them together, right? If I asked you for the total number of ions, I didn't say cations or anions, I said ions, plural, like ions, all of them together, you'd add them together, right? Does everyone follow that? What? I didn't hear you. Yeah, you're adding those two numbers together. Right? You don't have to tell me, but I just want to see if you know it. Okay? So there's one molecule of sodium chloride, one molecule of sodium, one atom of chloride, one atom of sodium. Yeah? Everybody with me? Yes. Does everyone follow this along? Yes. All right. So that's, I think, a great question. Now it's a long question. You know, on an exam, I probably would give you the molecular weight to make it shorter, and I probably wouldn't make you go all the way to ions, but I might. I have in the past. So please make sure you can do these kind of questions. They're not hard. If you want, just draw the little molehill to remind you how to do it. Okay, a lot of students do. They just draw it. First thing they do on the exam is they draw it, just so they don't forget. Okay? So that you can go all the way from grams, all the way to molecules, all the way to individual ions or atoms, just by knowing the formula and how much mass you have, okay? And a periodic table. Pretty cool, huh?
Awesome.
Good. I'm glad you said that.
So, quick question.
Yeah.
If this was a different, with the ion, what if it was a 3? It would be the same thing?
What do you mean, like it was Na3Cl? You have to multiply the Na by 3 then, because it's the 3-to-1 ratio. Okay, good question. All right, Try this one on your own. Nope, there it is. Okay, let me put the screen down. So, allyl sulfide, C6H10S. That's what makes garlic smell so good. How many moles of C6H10S are in 225 grams? So I want you to stop at the moles, don't go all the way to atoms. But just give that a try, see how you do. I'll grab a periodic table here and tell you the molecular masses here in a second. Okay. May I steal your book again? I promise I'll bring it right back. All right, carbon, hydrogen, and sulfur. All right, there are your molecular masses that you need to know. You'll have a periodic table on your exam. That's where they'll be printed when you need them. There you go. Thank you. Fred, the fire-breathing dragon. I learned that in high school. I haven't forgot it since. Where are you lost? It wouldn't be grams per mole though. Just be speak. See the grams, the mole, this mole here is actually right there. So I erase that mole.
Okay.
And you're not lost. You're doing fine. Keep going. Did you get it? I don't know what the right answer is, but I can. Looks right. Looks right. Good.
Going the right way?
Yep. Mm-hmm.
I am?
Mm-hmm.
Okay.
I don't know if it's right, but you're going the right way.
Oh.
Looks good. Where are you? Oh, there you are. Oh, okay. So you look like you did the right thing. You forgot the unit. You're missing something here. Okay, so this is the formula, C6H10S. So it actually would be 10 times 1.01 and 6 times 12. This is the correct procedure. You're doing this right. This number is just not the right number. So try that again. You didn't draw Fred. There we go. Got to have the fire-breathing dragon. Ooh, you're drawing like a vampire. That's actually better than a demon. How about a zombie? You know, because that's what everyone's into these days.
So yeah, so I did this.
Mm-hmm.
And I found out the molecular mass is C6.
Okay, you gotta be careful though, because the formula is C6H10S. So you have 10 times hydrogen, 6 times carbon. So this is correct. Your procedure is correct. This number here is incorrect. So just do that again and you'll get the right answer. Good job. Very good. Looks right. Don't know if it is, but it looks right. Did you round it right?
I think
So 3 6 figs. Yep, that should be right. Yes, ma'am.
I was wondering if I even did it right. 'Cause it's like,
You are in the right procedure, but I have no idea if the answer's right. But we'll figure it out. But your procedure is right. You might have done some calculations wrong, but you might not have too, right? Get it? Just don't forget your unit, that's all. Good? Okay, so here, you're on the right track, but that number is incorrect. And it's because it's going to be, if you look at the formula, it's 6 times carbon. And if you look at the formula, there's 10 hydrogen, so it's 10 times hydrogen and 1 times sulfur. So get that number corrected, change it here, and you'll get the right answer there. You got it. I mean, it looks right. The number could be wrong, but it looks right. Very good. Is this yours?
Yes.
You're welcome. It looks good. You look like you got it, but you stop here though. You don't have to keep going. If you want to, keep going, but you don't have to. All right. So, a lot of folks seem to have the right idea. There might be some errors here and there, but the idea, the concept is good. And if you know the concept, really, at least in my mind, getting the answer at the end is easier if you know the concept. Okay, so let's do this calculation real quick. So we have the molecular formula C6H10S, grams equal 225. And the mole is our question mark. So we have the molecular formula, we have the mass, we can easily calculate the moles. But we need the molecular mass. So we know 6 times carbon, 10 times hydrogen, 1 times sulfur. 6 times 12.01 grams per mole. 10 multiplied by 1.01 grams per mole. And what is this, 32? 0.70?
Why do you have 10 times 10?
1 time, what was the bottom one? 32.07 grams per mole. Add all that up, and what do you get?
Why do you have 10 times 10? 114? There you go.
What is it?
114?
2.
No, 13. I got 14. I got 13.13.
Point 2, 3. Is that the consensus? All right. Okay, grams per mole. Well, the committee is voting against you, so you got to argue with the committee, not with me. All right, so shh. Do I have to get my calculator out?
Yes.
One person says yes, no one else says no. The ayes have it. Next agenda item. That's life. Sorry. Even if you're right, you're wrong.
Oh, yeah, they're right.
Oh, see, now the ayes do definitely have it. Okay, so now we have the molecular mass, right? So now, with this number, we can relate grams to moles. So, let me erase Fred here, poor fellow. Time to go, Fred. Sorry. Let's figure out the rest of this question. So we have grams multiplied by something will put us into moles. We'll put moles on the top because that's what we need at the end. Put grams on the bottom. We know it's 114.23 and the number 1, and it's 225. So that divided by that gives me, oh, it's 1. Oh, okay, 1.96. 1.96 moles of C6H10S. How many sig figs are here?
3.
How many sig figs are here? 3. So no, you don't. Yeah. What's wrong with that answer? Because it didn't ask you to go to molecules, it said moles. Which is a great question, by the way. Stop. Stop. Everyone stop talking. Because everyone's muttering and I can't hear anybody. Is that answer not correct? I don't have a calculator, so I don't know. What is the correct answer?
1.97.
You guys are killing me. I should bring my own calculator. I never learn. But the thing is, I hate calculators. I just despise them. All right, here we go. Wasting more time here. So, come on, calculator. 225 divided by 114.23 equals 1.97. So whoever said 96, please see me after class. You owe me $15. There we go. If you don't round it off correctly, you will have lose 1 point on the exam. Make sure you round correctly. All right, so that is that. That wasn't that hard, was it? Except for the rounding error. Now, that will definitely be on your exam, so be prepared for questions like that. Probably be on your final, too. Now, chemical reactions. So we're out of the math for just a little bit. We're going to get right back to it, though, don't worry. Chemical reactions. For those of you who've taken lab with me, we've already done some of this stuff, so this will be like a rehash for you. But for some of you who aren't taking lab, this will be all new, maybe. It's not hard. It's not hard. Chemistry is a language. It's a language of symbols. We normally don't speak to each other in words. We use some words, but normally we speak to each other in symbols. If, for example, I were to take this reaction here, no matter if I was talking to a Japanese scientist, a Chinese scientist, an Indian scientist, European scientist, we would all agree on what this says. If we had this, C with a little S right there, plus O2, the little gas right there, there with a little triangle over top, you get CO2 gas. Just by seeing that symbology, all those symbols right there, any chemist and anywhere in the world can tell you exactly what that means. They may say it in a different language than English, but they all know what it means because we speak to each other in symbology because A, it's easier, and B, we kind of eliminate the language barrier. This is a chemical reaction. Over here are your starting materials. I put it in parentheses because that's kind of a slang jargon. Starting material. Over here, on the other side of this arrow, are your products. Products are usually what they're called. Sometimes you call it stuff or gear. But those are your starting materials or your reactants on the left, products on the right. Over here, the ones on the left, they're called reactants, but I almost always never call them that. I almost always call it starting material. Most American chemists and Canadian chemists will call it starting material. That's just what we call it. If we're going to write about it in a journal, we will call it reactants because that's proper. But we always just say starting material because that's what we're starting the reaction with. You know, shoot me, right? So now, these two things are going to add together to give me this product. Now, the carbon is a solid. That's what that parentheses S means. That carbon is in the form of a solid. Now, it's not saying which carbon it is. It's not, is it diamond or is it charcoal? You can bet it's charcoal because diamond's expensive. This one here is oxygen in the gas phase. So I took solid carbon, I mixed it with gaseous or oxygen in the gas phase, and they reacted to give me carbon dioxide gas. That's what those little letters mean in the parentheses. This little symbol over the arrow is heat. Now that arrow, that little delta symbol, doesn't mean that heat's produced. It means that heat was added. So when you start up this reaction, you have to actually light a match. This, for those of you who may not be familiar with this is a charcoal barbecue. When you buy charcoal from the store in your little charcoal Weber grill, you add carbon, which is charcoal, plus oxygen gas. You're doing it in the oxygen atmosphere of the earth. You light a match, starts the thing on fire, right? And then once the fire starts, it self-perpetuates. It keeps itself going because it gives off heat and flames. Okay? This is a barbecue. Isn't that cool? No. No, we don't like barbecues at all. No one likes those. Seeing the family running around at a park, no, we hate that stuff. It's a barbecue. Okay. Now, we've already learned about this, so I'm just going to go through it quick. Please don't try to write it down. Chemical changes is when you chemically modify something. If you take a piece of wood and you cut it in two, that's not a chemical change. It's a physical change. You just shorten the wood, right? It's still wood. If you take that same wood and burn it, it's no longer wood. You've chemically changed it. Remember all that? We talked about that before? Yes. That's a chemical change. So I want you to just remember that. Chemical changes. Here, we've changed the carbon and the oxygen chemically. We've changed it to carbon dioxide gas. When you change something chemically, its properties change. This was a solid, now it's in the gas form. This stuff is necessary for life. This stuff will kill you if you breathe too much of it. So it's changed it physically. And its properties are now different too. So now, which of the following is a chemical change? We've already done this, but I want to review it one more time. Which of the following is a chemical change? If you're burning a candle, is that a chemical or a physical change? It's a chemical change. Now the wax is melting around the flame, that's a physical change of the wax. But when the flame burns the wax, that's a chemical change. Okay? So burning a candle has two things going on at the same time, but the burning process is a chemical change. When ice melts, it's a physical change. You've gone from liquid to solid, or solid to liquid. When you burn your toast, tragedy. Yes, chemical change. Changes the flavor of the toast, doesn't it? The bread, if you eat it without toasting it, tastes like something. Toasted, it tastes better, right? Chemical change. Water turns to steam.
Physical.
Is that physical or chemical?
Physical.
Everybody.
Physical.
Physical. Doesn't chemically change the water at all. Okay. Write this down for me. I already talked about it, but I want you to have it written in your notes. The arrow indicates reactants from products. So the reactants are on the left, the products are on the right of the arrow. When you have multiple reagents, like we do on the left-hand side here, you separate them by plus charges. When you have multiple products, we don't. For this reaction, we don't. But a lot of reactions, you'll get more than one product. You'll just put plus. So this plus this gives you this plus that. Just the plus signs just tell you that there's more than one. The delta over that just means you're heating it. Just means you're warming it up. Okay? And that's all these things mean. But that little bit of symbology tells the reader a tremendous amount of information. Okay? Now, that's pretty neat, right? You know, symbology is kind of cool. Everyone likes symbology. Dan Brown made a living writing about symbology, Da Vinci Code and all that kind of stuff. So, you know, chemists are all about symbols. You know, this table here is a table of symbols, right? Which is, you know, kind of neat on its face, if you think about that. Okay. This is easy stuff, but it's stuff you have to know. What?
Those kind of questions make me dizzy.
Please don't pass out. If you feel the need to pass out, please let me know so I can leave. Everybody got it? Go quicker. Because this stuff's all posted online too, so if you do miss something, you can always get it online. Right? Okay. Got it. All right, good. All right, now don't worry too much about the top 3. Worry about the bottom 4. So write this down here. Solid, the S in parentheses is solid, the L in parentheses is liquid, the G in parentheses is gas. Those are obvious. This bottom one's a little different. AQ. AQ in parentheses is aqueous. Aqueous, E-O-U-S, yeah. Aqueous. Aqueous simply means dissolved in water. Aqueous, dissolved in water. So, one second. Don't forget your question. I'll come back to you. So when you're thinking about aqueous and what does aqueous mean, think about, what is that, astrology, with those little like Pisces and crap. Aquarius is the lady with the water jug, right? So aqueous simply means dissolved in water. Okay? So when you're drinking your Kool-Aid or whatnot, and you have, it's aqueous, it's like everything's dissolved in water, it's just aqueous. Okay? So that's all that really means. So write that down for me, please. Solid, liquid, gas, and aqueous, dissolved in H2O, water. Now you can dissolve things in other solvents, and those would not be aqueous because they're not dissolved in water. Got it? Pretty clear? All right. Let's move right along. Balancing equations. Now this is where the rubber meets the road, as they say. All this other stuff was preamble to doing this. Balancing equations. Now, when you balance a chemical equation, you have to follow what's known as the law of mass conservation, or the conservation of matter. When you start with something on the left-hand side of your arrow, it must be on the right, somewhere. Okay? When something's on the left-hand side of the arrow, it must be on the right-hand side, somewhere. Make sense so far? If you have 5 of something on the left, you must have 5 on the right. If you have 20 of something on the left, you must have 20 on the right somewhere. Okay? Now that doesn't make much sense until we do examples. Carbon plus oxygen gives me carbon dioxide. So now, to look at this question, you look at the reactants and the products. On the left-hand side, we have carbon. We have 1 times carbon. How many oxygen do we have? 2 times oxygen. And this is how I balance all equations. I start by just saying, what do I have on the left and what do I have on the right? On the right-hand side, I have CO2. How many carbons are in that molecule? 1, right? So times 1. How many oxygens do I have in that molecule? 2. Does everyone agree? Times 2. So on the left-hand side, I have 1 carbon, 1 times carbon, and 1 oxygen, O2. So 2 times O, because there's 2 of them, right? O2, it means there's 2 oxygens. Everyone agree? Yeah? On the right-hand side, I have 1 carbon, 1 times carbon, and 2 times oxygen. Now, let me ask you a question. Do my atoms on the left equal my atoms on the right of the arrow? Yes. That equation is called balanced. Okay? The stuff on the left equals the stuff on the right. Make sense? Everybody? Yes. So that happens sometimes. Sometimes you'll do a reaction and it'll do what I call self-balancing. You don't have to do anything special to it. It's already balanced. The atoms on the left equal the atoms on the right, and all is right with the world. Okay? Everyone so far happy with that? Okay. Let's move on to ones that aren't balanced and are a little more challenging. Here's one. Aluminum plus sulfur gives me aluminum sulfide. So now, we have starting materials. We have aluminum plus sulfur gives me aluminum sulfide. Now, on the left-hand side, over here, I have 1 times aluminum and 1 times sulfur. On the right-hand side, I have 2 times aluminum and 3 times sulfur. Does everyone see how I did that? Yes. Everybody? Yes. Now, we know it's not balanced because we have more aluminum on the right than we do on the left. We have more sulfur on the right than we do on the left. That's not good. That will cause a catastrophe of multitudes that we don't even want to fathom. So we have to fix this before the earth falls apart. Now, in order to fix it, well, let me just say something first. When doing this kind of question, or any kind of chemical question, do not ever change the formulas. So, for example, I wrote down Al2S3. Don't change that. No matter what you do, don't change it. I wrote down S here. Don't put S3 here because it's convenient. That will be wrong. Don't put a 3 here. No. Bad. Horrible. Don't change the formulas. Ever. Ever, 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 ever. Raise your right hand. Everybody, raise it. I pledge to not change the formulas in balancing equations. By risk of failure on exam. Okay. Now, that's kind of funny, right? We do that because it's fun. But I'm telling you, you've all said it. You've all promised you won't do it. 4 or 5 of you will do it on an exam. You just will. That's my experience. Please don't, because it will get the whole question wrong. And it will make the question impossibly difficult to figure out. Okay? So now, here's how you do it. I have 1 aluminum and 2 aluminums. So I have 2 here and only 1 there. In order to balance it, I have to somehow indicate that there's 2 aluminums here. I don't put a 2 here because that's changing the formula. I put a 2 in front of the aluminum. The same font size as the aluminum. Like, don't make it big and don't make it small. Make it the same font size. Now, I'm not going to measure it with a ruler. If it looks about right, I'll mark it right. But now, if you put like aluminum and then put like a little 2 right here, I'd mark that wrong. Because, you know, that's not right. That's like weird. Make it the same height, 2. Again, don't worry about getting it exactly right. I'm not going to measure it, you know. But as long as I have an idea that you know it should be the same height as the aluminum, that'll be great. Okay? So now, while you're doing these, whenever you make a change, like you put a number in front of something, go back and reevaluate the entire thing. Because on this one, it won't do much because it's a very simple question. On some questions, changing one thing changes 3 or 4 downriver. So you have to be very careful of that. So now, we've put a 2 in front of the aluminum. So now that means I have 2 aluminum. If I were you, I would do these questions in pencil. Why? Because now you have to erase this 1 and put a 2 here. I have 2 aluminums, 1 sulfur, 2 aluminums, and 3 sulfur. So I've done a good thing. I've balanced one of my elements. So I balanced the aluminum. Now the sulfur is not quite right. I have a 3 on the right, and I only have 1 on the left. So what do? Put a 3 in front of the sulfur. Now again, do these in pencil, especially when you're first learning them. Because you're going to make a ton of mistakes. And don't let that discourage you. That's part of the learning process. I can do these in my sleep, but I've been doing them for 25 years. You guys are new, so allow yourself to get them wrong. Don't worry about it. Go back and try it again until you get it. Once you start figuring it out, and like they start coming to you like almost automatically, you'll fly through these on an exam. You really will. But you got to practice them. Okay? All right, so that's a pretty good one. That's a pretty simple one. Let's try a harder one. These ones are boring.
Would you,
Oops. Let's try that one.
learn what caused what reaction?
Say that one more time.
Are we going to learn what caused what reaction?
What causes a reaction? We're not going to learn too much about that because it's rather complicated. But we are going to learn a little bit about what causes reactions to happen. But in order to actually understand what causes a reaction, you really have to take a lot more chemistry. Because even some chemists don't understand what causes a reaction. You know, sometimes it's energy, sometimes it's just other factors.
So the final answer would be 2 times AL times 2.
No, the final answer is written on the top. 2Al plus 3S plus Al2S3. That's the final answer. The stuff on the bottom is to help you figure out how to solve the stuff at the top.
Okay.
If you have your own approach, you don't have to use mine. Let me just say that again. If you have your own approach to solving these problems and you like it and it gets you to the right answer every time, don't worry about learning my approach. I'm not going to mark you on the approach. I'm going to mark you on the correct answer. Okay? Like these kind of things, a lot of folks, if you're good at them, you can do them in your head. But if you're not good at them, it might take you some time. And this is a systematic approach to get to the right answer. All right, let's try this one. It's a little bit tougher now. Whew, man. Iron 4 oxide. Whoa, holy smokes. Let's try this one. This is tougher. But we can do it because we have a systematic approach. Iron 4, wow. Iron 4. Fe3O4. That can't be right. Huh, whatever. We'll use it. I don't think that's right, but we'll use it anyway. We'll make it work. Plus hydrogen gas will give me iron plus water. Okay. So now, how I would start this is I would just say, okay, on the left-hand side I have 3 times Fe, 4 times oxygen, and 2 times hydrogen. That's the left side. So the 3 times iron goes there, 4 times oxygen goes here, and 2 times hydrogen goes there. Pretty simple? Over here we have 1 iron times 1 times 1 and times 2. Well, looky there. Hydrogens seem to be balanced. We all raise our hands in victory, but I don't think it will be balanced for long. The irons and the oxygens are out of whack. Now, as a general rule, doesn't always work, but as a general rule, whenever you have a single element by itself, iron's all by his lonesome, balance him last. Balance everything else and then balance him last. Okay? Why? Because if you go ahead and balance the oxygen last, or sorry, if you balance the iron first, you put a 3 here, well, the oxygens are still out of whack, right? So you have to balance the oxygen, and that might throw the irons out of whack. So balance the iron last. It's just simple. There's nothing else here. It's just iron. You're just going to put a number there and be done. Okay? Okay, so let's try balancing. Well, the oxygen's the only thing that's left, right? We have to balance the oxygen. Okay, so we have 4 oxygen on the left. Yes? We need to have 4 on the right. So what do we do? Right. Now, some of you want to put the 4 right here. I'm going to see it. I always see it. Somebody wants to do this. And you've already pledged that you won't do that. So don't put the 4 there, because that makes your life easier, but it also makes the question wrong and impossible to figure out. So don't put the 4 there. That's completely, totally wrong. What you want to do is put the 4 in front of everything. What that means is, in this reaction, so far at least, we're going to form 4 water molecules. Are you with me on that? So now. Aha! That's why I say whenever you make a change, go back and review everything. Okay? So we made a change, so now we say, okay, 3 iron, 4 oxygen, 2 hydrogen. Nothing changed there. 1 iron, wait now, just as you said, hydrogen. is 2 times 4. Now there's 8 hydrogen, isn't there? Okay? So you have to erase this. We have 8 on the right-hand side now. Are you with me on that? So that the hydrogens now aren't balanced. So now we have to balance hydrogen. On the right-hand side we have 8. On the left-hand side we have 2. What do we got to do here? Put a 4. Where do you want to put it? Front of the hydrogen, right here, right? Does that make sense? Everybody? Okay, so we made a change. So go over it again. I know this seems redundant, but I'm telling you, you'll be happy you do it.
The oxygen there be 4 because you already put the 4 in front of the H2O.
Ah, you're right. I'm sorry, I didn't change it. I get excited. Sorry. Now, we put the 4 in front of the hydrogen, so let's go over the whole thing again. Iron is 3. Oxygen is 4. Hydrogen now is 8. Pretty neat, huh? Iron is 1. 8 hydrogens, 4 oxygens. Ha-ha! The only thing left to do is balance iron. And all we got to do is put what number right here? 3. So that makes this a 3. Now, as a final check, when you've got everything done, you think you're done, you think it's groovy, everything's perfect, go over it really quick. I have 3 irons on the left-hand side. So go over to the right, 3 irons on the right. You with me? I have 4 oxygen right here, 4 oxygen right there. You with me? 2 times 4 is 8 hydrogen. 2 times 4 is 8 hydrogen. That equation must be chemically balanced because all the numbers add up. Is that pretty neat? Okay? Yeah?
So will all equations be balanced?
All equations are balanceable, but they may not be balanced. Like if I give you an equation, the first thing you want to check is that it's balanced. Okay? Good question. All right. Balancing equations with polyatomic ions. Now, this one's already balanced for us, so they kind of just gave us the answer. But let me go over it with you on how you would do it, how you would approach it. It's even, right? Hold on a sec. 6 sodium, 6 sodium, 2 PO4, 2 PO. Yep, okay. Yep. Okay, let me go over this for you on how you would balance it. I'll give you a few tricks of the trade to help you out. So there we got sodium phosphate plus mag chloride goes to give me Mg3. Yeah. Okay, now it's already done there, I know, but I wanted to show you some tricks. Looking at that equation, we could do the following. We could say, okay, there's 3 times sodium, 1 times phosphorus, 4 times oxygen, 1 times magnesium, and 2 times chlorine. And there's going to be 3 magnesiums here, 2 phosphorus there, 8 there, 1 there, and 1 here. Wow, that's a lot of stuff happening all at once. It's simply just a lot, right? Now, there's a simplifying way to do this. We notice that here we have a polyatomic ion, PO4. We also should notice that over here there's a PO4. So from left to right of the arrow, the PO4 didn't change. The polyatomic stayed the same. Did everyone notice that? Everyone with me on that?
Yes.
So it's important that you can identify polyatomics. If you can't, these become harder. So now, the polyatomic hasn't changed from left to right. So if that's true, we don't have to say, what's that craziness? There we go. We don't have to say 1 phosphorus times 2 and then all this stuff. We could say over here there is 1 times PO4. And over here there are 2 times PO4. We don't have to say any of this stuff right here. Just ignore it. There's 1 PO4 over here, 2 PO4s over there. Instead of treating them as separate atoms, treat them as one unit. Makes life so much easier. Okay? So treat the polyatomics as long as they stay the same from left to right, as long as they don't change, treat them as one thing. So 1 PO4 on the left, 2 PO4s on the right. So let's just make that look a little bit prettier. Get rid of all this stuff that's making me nervous. Put the PO4 right here, times 1 times 2. Now, that's the first thing. The second little hint is when you have polyatomics in your formula, balance them first. It almost always works to your advantage to balance the polyatomic first. Now, I'm not saying it will always work, but I can say from my experience, I've never had it go wrong. So try it that way. So I'm going to balance my polyatomic first. So here I have 2 PO4s. So over here I have to have 2, right? So what do? Put a 2 in front of the sodium. I like that. So I'll put a 2 right there. Now, I have to go over the whole entire formula or the equation again to make sure I don't miss anything. So now I have 2 times 3 sodium. So that's 6, right? So my sodium, where are they? There, is now 6. My phosphates, PO4s, are now 2. Magnesium and the chlorine stay the same. On the right-hand side, I have 3 magnesium, 2 phosphate, 1 sodium, and 1 chloride. Okay. Still not balanced. Wow. Well, now what do? Well, it doesn't matter. Pick one.
Balance the sodium.
Balance the sodium, she says. I have no reason to say not to, so let's balance the sodium. On the left-hand side, we have 6. Here we have 1. What do I got to do? Put a 6 right there. So now I have made a change. Go over everything again. 6 sodium, 2 phosphates, 1 magnesium, 2 chlorines, 3 magnesium, 2 phosphates, 6 sodium. 6 sodium, and now 6 chlorides. See why I go over everything? So I don't miss anything. Okay, now my chlorines are out of whack. It's like pulling your hair out. Frustrating. Now what do? Put a 3 where? If I put a 3 here, does that help me?
Yes.
Does it? Well, let's check. 6 sodium, 6 sodium, 2 PO4, 2 PO4, 3 times 1 magnesium, so now I have 3 of these. Hope that helps. 3 times 2 is 6 of those. Well, my chlorines are balanced now. So 3 magnesium, 3... Wait a minute now. Hey! Magnesium balanced by itself. Isn't that nice? 2 PO4s, 6 sodium. Where's sodium? There it is. 6 chlorine. It appears to be balanced, but I'm not going to take that for my final answer. I'm going to review it. 2 times 3 sodium is 6 sodium. I have 6 sodium right here. So that's pretty good. I have 2 phosphates right here. 2 phosphates right there. Got my fingers crossed that this is going to work out good. 3 magnesiums right here. 3 magnesiums right there. Isn't that cool? Balanced itself. 3 times 2 is 6 chlorine. And I have 6 chlorine over there. I am very happy that this reaction appears to be balanced. I think I've done it right. Now, when you have an element by itself, balance it last. So if you have a lone carbon or a lone iron or whatever, balance it last. Balance the polyatomics first. Okay? Use a pencil. Don't be frustrated if you make mistakes. Keep trying. It's easy. Think of it as a puzzle, not as a problem. All right? Work on these, and I will see you all next week. Have a great weekend, everybody.